Good morning. Welcome back for another lesson in Math 8. Today we're on Unit 2, Lesson 4, working with dilations on a square grid. Today we're going to be figuring out how to do a dilation using an actual grid system. We're going to review a little bit about what it means to use a scale factor, and we're going to be able to see what it looks like when figures grow and shrink according to the scale factor. So first off thing we're going to start here is point C. We're going to estimate a scale factor. So point C is a dilation of point B with center A and scale factor S. We say scale factor S because we don't know what it is, and we're supposed to estimate what that value would be. Now, what we can do with this, there's a lot of ways we can do this. We can kind of use the age-old eyeball test to kind of look and see, well, what does that look like, and try and decide. Or we can use a piece of paper, but what we're not going to use is an actual measuring device for that. So what I'd like to do is just go ahead and use, to start out, I can look at this and I can see pretty clearly that the distance from A to B, sorry, I guess I better back up. Point C is the dilation of point B, meaning that if C is out here and A is the center, then we're growing from A to C. And when we know that there's growth, we have to remember that when we see growth, we know that our scale factor is going to be greater than 1. All right, so we know right now that this is growth, so we have to have a scale factor that is greater than 1. We have a couple ways that we can estimate the distance here. I noticed something when I was playing with my pen earlier, that the top of the cap to this line is about the same distance from A to B. And when I set up that distance again right here, this would be twice as far away, or a scale factor of 2 would come in approximately right here. So I know right now that my scale factor, when we're talking about the distance, this will be a scale factor of 2, but then I have this little tiny chunk that's left. Now, when I flipped my pen around, I noticed that the top of my pen, the tip from here to here, is going to be about the same distance from here to here. And so I kind of played with that a little bit, and I thought, you know what, how much of that little distance is covered from here to here? There's 1, and then I just played with them and marked them out all the way across, and I noticed that the tip of my pen was, or this length, was 1/3 of these distances. So by looking at this, I can actually come up with a couple of pieces with it, or a couple of estimates. So again, scale factor, my estimate on this one is about 2 1/3. I could do the same thing when I'm talking about a distance on paper. Going from A to B is about that long. And we'll see that very similar things happen for paper from here to here. And then I look at that little teeny tiny piece right there, and again, I can set that all up. Perhaps you wanted to say that it's a scale factor of 2.5 or 2 1/4. 2.5 would be a little bit too big. 2 1/4 would be more reasonable, but estimating that scale factor can be done in numerous ways. If we wanted to get exact, that's when we would pull out a ruler and we would get those measurements. When I look here to here, this is 3 1/4 centimeters. When I look all the way out at the full distance, 3 1/4 would be 7 1/2. And if I look at the distance here to here, there's 7, and we're looking at another 1/2 of a centimeter. So my reality is that this is pretty darn close. Let's get to the fun stuff. When we talk about dilating on a grid, we're talking about actually growing and shrinking from a given point. In this case, we have quadrilateral ABCD that has a center of P and a scale factor of 2. Recognizing that we have these pieces, center P, scale factor 2, helps us to realize that this shape right here should increase in its size, and not just its size, but what we really want to focus on when we talk about the scale factor is we want to talk about distance from center. So when we talk about the distance from the center, there's consequences that happen with that, but it all goes back, and as far as the growth, it all goes back to the distance from the center. When we look at the distance from center, we take a look from here to P. We're going to go ahead and measure that distance from P to A using our ratio of rise over run. So we're always going to be talking about vertical change and then horizontal change. So this one right here, from P to A, we see that we go up 1, 2 units and left 1 unit. So when we look at that distance of 2 over 1, and to the left, we call the left going to be negative values. So moving to the left, when we double that, what we're looking at is 4 over negative 2. We see that those ratios are exactly the same ratio, but we're just moving further away. And so from P, we want to count up 1, 2, 3, 4, 1, 2. And this gives us A prime. The other thing I could do is just use the same ratio twice, rise 1, 2, left 1, 1, 2, left 1. And we see what happened here is the distance of point A has been translated further away following that same ratio. We see this distance here has been doubled. We would do the exact same thing for P to D, and we would see a rise this time down negative 2. We're going to call this one A. And here's D. We're going to go down 2 units, 1, 2, and left 1. So we would see negative 2 over negative 1. And we're going to double that distance because of the scale factor 2 to making that negative 4 over negative 2. So here we go. 1, 2, 3, 4 down, left 2. And we get D prime. Again, I could have just gone down 1, 2, left 1, down 2, left 1 to repeat that pattern. And we will see that exact same pattern used for B and for C. So here we go. For B, this is up 2 units. And to the right, 1, 2, 3, 4, 5. I'm going to go ahead and grab C real quick. Down 2, to the right, 5. And then we double those. We know that that will be 4 over 10 and negative 4 over 10. So down 4 units. 4, 5, 6, 7, 8, 9, 10. There's C prime. And then B, we go up 2 to the right 5, 1, 2, 1, 2, 3, 4, 5 for B prime. Now, if I did this right, my figure should look exactly like the other one, only smaller. All of my angle measures should be exactly the same. So when we talk about dilation, we want to be able to see and we want to know the angle measures of the figure are preserved. But the lengths of the segments are not. Instead, they're grown proportionally based on the scale factor that's given. So all of the sides will continue to grow or shrink according to that proportion given by the scale factor. Now here's one of the consequences that we can see. We can see that the distance from P to A is half of what it is from P to A prime because we saw growth. We can see that these points from P through A to its image are collinear, meaning that the center of dilation to its original point and out to the dilated point are all going to fall in the same straight line or same ray that can go from that center of dilation out. And we see that growth coming from it, and these distances are just the exact same, or excuse me, they're just double the distance. Another interesting fact that we can see is that not only did the distance from the center of dilation to the point double, but also the length of each side. So this one right here is 4 units long. We look at the length of segment A prime, D prime, and we see that it is 4, and then 4 more for 8 units long. And we can see the same relationship from A to B. We see that A to B is 6 units long. And we see from here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The cool thing about recognizing this is when we go ahead and do our work, we have a way to be able to come back and to kind of have a fail-safe to check to see, did I do my work correctly? So let's go ahead and look at another example here. We have a triangle QRS, that is being dilated from center T with a scale factor of 2. And then we're going to go ahead and dilate that same triangle with the center T and a scale factor of 1/2. We can see that there's rays that are already drawn for us. And as we do this dilation, we are going to follow this same ray to grow point Q further away when we do a scale factor of 2, and to shrink it back to T when we see a scale factor of 1/2. So let's go ahead and look at these pieces. When we talk about growing out to Q, we have a ratio of rise 1, run 3. And then when we double that, we want to get for Q prime from T to Q, we want to go ahead and, whoops, I wrote the wrong ratio, 1/3. We want to double that to 2, 6. Notice that the ratios are proportional. They are equal to each other. And so we can just do that same steps. 1, 2, 1, 2, 3, 4, 5, 6. And you'll notice that when I follow that ratio, I hit that ray that comes out from the center of dilation through the original point and our new point, or what's called collinear. So there would be Q prime. Follow the same thing with T to R, T to S. We have it down for T is down 1, right 4. Doubling that will be down 2, right 8. And then S, we have down 2, right 2, which makes S prime down 4, right 4. So we can continue that pattern. And we notice that we end up on that same line every single time. Excuse me, on that ray every single time. And then we just take a straight edge and draw our new figure. And what we notice, or what we should notice, is that these distances from here to here are double the distance from what they were. If you look at this one, rise 1, run 2 for S to R, rise 2, run 4 from S prime to R prime. Those distances are doubled, but the angle measures are preserved. Now, what about when I go smaller? Well, the same type of thing, only for S. Let's go ahead and start down here on S. We had down 2 over 2, but our scale factor is half, so let's go and take half of those measures. We're going to call this one S double prime since we're using the same diagram. And we're going to go down 1 this time and right 1 from T. So we'll come down 1, right 1 from T, and you'll notice there's that same ray being used again that has now all 4 of these points are collinear with each other. And all the time when we're doing a dilation, we have to see that collinear relationship. So we can look at R was down 1. Oh, I see another mistake I made. T is the center of dilation. That's point R. R was down 1 to the right 4. Half that distance is going to be a negative 5/10 over 2. So how would I do that one? Well, again, I want to be able to go just down half, but maybe I don't know exactly where that is, but that's where this ray comes in very handy. I know that this is 2 units to the right. I know that my point has to be on that ray, so I know that point R prime, or double prime in this case, will have to be right here. And then we look at point Q, which was 1/3, or it was up 1 to the right 3. Half of that is going to be up half a unit and over 1 1/2 units to the right. And so this one might be just a little bit trickier. So we're going to go up half unit and then over 1 1/2 units. So we're just going to look right here at the center of this box. We call that one Q double prime. Again, make our lines. So now I want you to notice one more thing. This side QS and Q prime S prime, if you notice, these segments are actually parallel to each other. Under the dilation, if I don't dilate this correctly, I won't see that relationship parallel. So there's another thing besides just looking at does it fall on the rays and is the distance doubled or halved or whatever the ratio is for the scale factor. But there's another thing right there to recognize that, hey, those sides, they need to be parallel to their original sides. Otherwise, I'm also not growing at a correct rate. Now, right here, we're not going to get absolutely perfect, but we're going to get as close as we possibly can. And you can see that that triangle looks like from point T is just continuously growing larger and larger and larger as we get farther away from the center of dilation. And as we look at getting closer, it's closer and closer and closer. But again, it's proportional. So keep that in mind. Dilations must be proportional in their growth, whether it's getting larger or getting smaller. Now, the last part of our lesson, what happens if we give you a circle? Oh my goodness, a circle. That's got to be a lot harder, right? Oh, maybe not. Let's look and see what we're looking for here. It says the image of a circle under dilation is a circle. Well, that makes sense because if we're just shrinking or growing something, a circle will just get larger or smaller. So when the center of dilation is the center of the circle, what happens if the center of dilation is a point on the circle? Wow. If it's a point on the circle, what we need to remember is that the center of dilation is always that single point where everything is growing away from or shrinking back to. It's kind of like a yo-yo when you're dropping it down and up. It's all connected to your finger, so it's always going to be the length of that segment, or the length of the string is always going to get longer and shorter, but it's always going to come back to that one single point. What we're going to do right now is we're actually going to use center 0, 0 and a scale factor of 1.5. So here's our center of dilation 0, 0, scale factor 1.5, and we're going to dilate the circle as shown on the diagram. And we have a few points that are going to help us. Let's see how that works out for us. When we look first at point C, 1.5 times greater. Right now I have my rise or my run. I'm going to show you a little bit different way of what we can do with this. What we see is that this ordered pair, point C, is at 5/10 and 2. When I want to go to C prime, what I need to do with this is I need to take my scale factor and I want to multiply both of these figures, the original 5/10 times 1.5 and 2 times 1.5. Both of these are distances from that center of dilation. We have two distances because we're on a coordinate plane. We have the distance along the x coordinates or the x-axis and our distance from the y-axis or along the y-axis. So now we want to see how that growth works. When we look at half and we multiply that by 1.5, we can go ahead and use a calculator here. And we see that our distance is actually going to be now at 3/4 of a unit away. So we see C prime is at 3/4 or 75/100. And 2 times 1.5, well, 2 times 1.5 is going to be 2 times 1 is 1. And 2 times 1/2 is, or excuse me, 2 times 1 is 2. And 2 times 1/2 is 1. So we should see that 2 times 1.5 is 3. Very good. That's what it is. Nice job, Quilter. And so there's our new ordered pair that we'll go ahead and graph on the coordinate plane. So in this case now, we're going to go to the right 3/4 of a unit and then up 3. But then again, there's that question of, well, Mr. Quilter, I don't know exactly where 3/4 is. So let's go ahead and use that strategy that we used before of creating a ray that goes from the center of dilation through each of these points. So we're just going to quickly and gently sketch these in, just nice and light. We're going to do from C or to C, point C, and then to point H, then to point D. That looks like it's going to be quite a ways away, so I may not have enough there. And point G. And then we're going to go ahead and quickly calculate these values and go ahead and draw these on. So I know 3/4 and 3. What I'm going to do with this is I'm actually going to come over to where I think 3/4 is. I'm going to rise up to where 3 is. I'm going to look here on my ray, and I know that that has to be the correct point because my dilated points have to be collinear or in a straight line with the original and the center of dilation. Looking at this next one, point H, that one looks a little bit funny. That looks like it's at 3 and then just under 4. So I think that H is at 3 and about 3 9/10. It's not very friendly, but it's what we have to work with. So we'll do the same process then. We'll take C prime and we're going to go ahead and multiply the original x coordinate times 1.5. And then we're going to multiply the original y coordinate by 1.5. So both of them being the distances have to be adjusted by the scale factor. And I shouldn't be calling that C prime. I should be calling that H prime. So we'll go ahead and go back to our calculator. We're going to see 3 times 1.5 is 4.5. 3 9/10 times 1.5, 5 and 8500ths. Those are not very friendly, are they? But it's what we have to work with, and we can do this because we're mathematicians and we know how to do this. So H, we're going to go over to 4.5, and then we're going to rise up until we get to that 4.5 mark where we hit the ray, and we'll see that we're going to go approximately right here, H prime. Now, for the sake of time, I can continue to do the same thing, but I want to show you what happens as I look at these pieces right here. What I should be seeing is the same kind of growth right here. I should be seeing the exact same arc because we know the angles are preserved when we're talking about angle measures anywhere from 0 to 360. But when we're talking about an arc on a circle, we actually can't forget that that arc is a type of angle. And so we have to remember that that same curvature is going to be preserved as well. Now here's the hard part. As we get further away with our dilations because of the center dilation and our scale factor, it actually gets a little bit harder to figure out exactly where that arc is. And so what we would need to do is we would need to identify several more points along the original shape and continue to do the same process that we've been doing here to be able to get a nice dilated curved figure that's going to help us to actually see this arc become the exact same as what it was in the original. So curved figures, a little bit more challenging, not impossible. All it takes is a lot more points to be able to make sure we get a nice dilation done. So with that said, here we are at our summary. Square grids can be very useful when we're talking about dilation. The grid is really helpful, especially when the center dilation and the points are being dilated when they're on that grid, because instead of using a ruler, we can just use the ratios of rise over run, or what we're going to come to know as slope. So we can just count the grid units. When we look at that and we're looking at this piece, say we're dilating from point P to point Q, and then Q is being dilated a little bit further away, we can see that since that distance, point Q prime, is further than P, we know that the scale factor must be greater than 1. When we look at our directions, we see that here's point Q is dilated from center P, scale factor of 3/4. Since Q is 4 grid units left and 2 grid units down, we would see that that dilation 3 halves further, meaning that 2 times 3 halves and 4 times 3 halves would take us down 6 units to the left, or 3 units down and 6 units left. When we're working on a coordinate plane, I really like working with the coordinate plane because I can see it from that other piece, that other perspective of using the exact same strategy of dilating by up and down and left and right, only using coordinate points or coordinate pairs. So in this case, dilating from center 0, 0. Oh, by the way, that's a big thing right here, is anytime we're dilating from center 0, 0, this works. To be able to just take the ordered pairs and dilate by multiplying by 2, you'll see that this one, -2, -1. So right here is being dilated by a scale factor of 2, -1 times 2 would be -2. We're going to do this. We're going to call this one point A and A prime, B, B prime, C, and C prime. And we see that the relationship exists all the way across. -1 times 2 is -2. -2 times 2 is -4. 3 times 2 is 6. 1 times 2 is 2. 2 times 2 is 4. -1 times 2 is -2. You see the pattern. But this pattern, when I multiply the scale factor by 2 or 3 or 1/2 or what have you, we can only use this strategy of just multiplying the ordered pair by the scale factor when the dilation is with the center 0. The same practice will hold true when the center of dilation is not at 0, 0, but we may need to go back to this strategy here about just taking our distance from one point, going up to right 4 or what have you. The last part of it is actually, that's the next lesson. But you can see where we're going to be looking at is we're going to be seeing the same kind of growth. But that's it. Dilating with a square grid is actually really quite easy, in my opinion. I hope you have fun with it when you take a look at it. Make sure that you just give me your best today and have fun doing the homework. Thanks for your hard work. Watch for that homework help here in just a few minutes. Have a great day, and don't you dare give up.